Hello, and welcome to the module BJT Basics Current Amplification. In this module, we're going to be talking about our motor driver circuit. Now, in previous modules and labs, we've already analyzed our motor, and so we know that it takes a DC voltage input and outputs some encoder signal which tells us how fast the motor is going. We've also built a speed sensor circuit which takes the encoder signal and generates a voltage proportional to our motor speed. Now in a future lab, what we're going to do is build a feedback circuit which is going to take this voltage proportional to motor speed, compare it to some reference, and give us commands to drive our motor to whatever speed we like it to be at. So this feedback circuit is going to output two control signals seen here. And what we need is some way to turn these control signals into the DC voltage that our motor is going to take. And we're going to do that with our motor driver circuit. Now internally, our motor driver is going to look something like this. It's a BJT based motor driver. You can see here we have 4 BJTs, each of these devices. We have our two control signals from our feedback controller, B1 and B2, and these are low current control signals. These aren't driving a lot of power. They come from a simple feedback circuit, which in our case is eventually going to be an Arduino microcontroller. What we would like is for all the voltage and the power that's driving our motor to come from our DC supplies. So we'd like our current flow to be something like that, from our DC supplies, not from our control signals. And we'll hook the motor up in the center here and be able to supply it with anywhere from between 10 volts to minus 10 volts. Now to understand how these BJTs work, let's first take a look at a diode. Remember, there's a number of different models for these diodes. We have the ideal model, which just is an L-shaped line. Tells you that if you have forward voltage, you're going to conduct forward current. We have a constant voltage drop model, this orange line, which tells us that there is going to be some forward voltage that we need to overcome in order to have the diode conduct. Sometimes we call this the knee voltage. And then slightly more precise is the piecewise linear model, which gives a slight slope to this current line as we apply more forward voltage. And that tells us that the more current we have through the device, the more voltage drop we're going to see across it. Now all of these lines are just approximations for the actual diode operating line, as we can see over here. You can see that if we do have forward voltage, we are going to start conducting forward current. We have some knee voltage. It's 0.7 volts to 0.8 volts for a silicon diode. And we have what's actually an exponential line here, increasing current as we keep increasing the voltage. In addition, we have a reverse region, which most of our models ignore. And you can see that we do block current for most of the reverse region, but eventually our diode's going to break down, and we'll see this increase in reverse current as our diode passes its breakdown voltage. Sometimes this is a destructive process, sometimes the diode can recover from it, but in general it's not a good place to operate your diode. Now, physically, a diode's put together with two pieces of silicon, one N-type and one P-type. And so you have this sandwich of N-P-type silicon creating your diode with current flowing from the P-type towards the N-type. If we take a look at a bipolar junction transistor, and this is an NPN bipolar junction transistor, you'll see it looks a lot like the diode in physical device structure. Here we have one PN junction, and here we have another PN junction. So it looks like two diodes stacked back to back. Now if we connect control ports to these three places, we end up with a 3-terminal device, since the bipolar junction transistor. We name these the base, the emitter, and the collector. And we'll draw a symbol for this device as you can see here. Notice that this is an NPN type device, and so there's this little arrow pointing out towards the emitter. That's because generally you'll have current flow coming this direction following the arrow. Now we can get a couple of different operating modes for this device dependent upon the relation between the base emitter and collector voltage. You see here we've defined V base emitter and V base collector, and we've plotted them right here. Now if the base is much lower than both the collector and the emitter, and so we have maybe even a negative base collector or base emitter, we're going to be in the cutoff region of operation. Now in cutoff, our device is going to look like an off-state switch, so it's going to look like an open circuit. In general, if a device is in cutoff, we can simply remove it from the circuit completely. If the other case is true, and the base is much higher voltage than either a collector or our emitter, or than both of them at the same time, we're going to be operating in the saturation mode. In saturation mode, our BJT is going to look like an open or an on-state switch, and so it'll look almost like a short circuit between collector and emitter. The third mode is the one that we're going to use, and this is the active mode. In the active mode, the BJT looks like a current amplifier. And this is what we'd like to do, because remember, we don't want all of our current to come from our control signals. We want it to come through our BJTs from our voltage supply rails. And we can do that by using these as a current amplifier. Now to operate in the active mode, we need a low or negative base collector voltage, meaning our base is going to be up near our collector, maybe a little bit higher than it. And we need a positive base emitter voltage. So we need our base to be at a higher voltage than our emitter. Now when you see a BJT in circuit, simply try and determine what voltage all the ports are going to be at, and that'll tell you what mode it's operating in. When the BJT is operated in active mode, we have a nice equivalent circuit for it, and you can see that right here. So for an NPN type BJT operated in active mode, we can simply replace it by this small circuit whenever it comes up. You can see here we have our base emitter diode, and this is just a silicon diode. You can see it on the physical device, base emitter diode. It's that PN junction right there. So we have some base current coming through that, and then we have our current amplification right here. You can see our collector current is going to equal beta times our base current, and beta is generally in the range of a couple hundred. So from the devices we use, beta is going to be about 200. And you can see just how much current amplification we get there. So we're going to have 200 times the current coming through here as we have flowing there, which is exactly what we want. Now if you simply take the construction for an NPN type and switch P-type with N, we have a PNP bipolar junction transistor. You can see it's almost the same thing, but instead of NPN we have PNP up here. Again, we label the base, the collector, and the emitter. As you can see here, base, collector, and emitter. But we treat the PNP bipolar junction transistor as the dual of the NPN. What that means is that instead of base emitter voltage, we have emitter base. Instead of base collector voltage, we have collector base. All of our voltages are inverted. You can see here we draw the line up top here for a PNP type. And even though everything's inverted, we still have the same three operating regions. We have cutoff, which looks like an open switch. Saturation looks like a closed switch. And active mode, which gives us our current amplification. Now because this is a PNP type and not an NPN type, we have a slightly different equivalent circuit here for the PNP operated in active mode. And if you compare this to the one on the previous slide, it really is just everything flipped upside down and reversed in polarity. Again, we have our emitter base diode right here, just a silicon diode, and that's this PN junction right there. Then we have our current amplification. Same thing, IC equals beta times IB. So 200 times or so the current coming through here as we have going through there. And that's generally how these BJT transistors work. Make sure you recognize which type of device you're working with, because it does make a difference in terms of what voltages you need to get into which operating region. So when we put these all together as a motor driver circuit, we have this circuit we've looked at before. We have our 4 BJTs. Here you can now see what type they are. We have 2 NPN type, Q1 and Q2 are NPN type, and Q3 and Q4 are PNP type. What we'd like to be able to do is apply a voltage to our 2 control ports. These are our control ports from some of the previous figures right here, and have that cause some current to flow through our motor. So let's just take a look at what should be the maximum current case through our motor. We're assuming this is the maximum current case because we tied one of our control signals to 10 volts and we've tied the other one to 0 volts. So we have the maximum difference between those two. And we're assuming that we just have a resistance modeling our motor. This is that R motor, somewhere on the order of 2 ohms. We should get the maximum current in this case simply because this is the model for our motor, which will allow the maximum current. It's the locked wheel test, which we performed in lab. So now just looking at these devices, we can start to think about what operating mode they must be in. So let's take a look at Q3 first. And we'll notice that Q3 is a PNP. We'll notice that for Q3, here we have the collector and the base. The collector is at 0 and the base is at 10 volts. What that means is we have a very negative collector base voltage. So we're going to be operating somewhere down here. We're really far down this line. And then, since we're either in cutoff or active, we have to take a look at the emitter base voltage to determine which it is. Again, you can see our base is at 10 volts. To get active mode, we would need our emitter to be above our base voltage. We need a positive emitter base. But since our base is at 10 volts, it's pretty unlikely that this node here is going to be above our highest voltage rail. There's really no way for it to get above there. There's no other source driving it up there. So we can safely assume that we're in the cutoff region. So Q3 is in the cutoff region and we can simply remove it from the circuit. Q2 is going to be in cutoff as well, going through the same analysis. Now if we look at Q4 down here, let's simply draw in the ports. We have base, collector, emitter right there. Our base collector voltage is going to be 0. So we're going to be somewhere here. We're on this line somewhere, right, depending on our base emitter voltage. Take a look at our base emitter voltage. Well, our base is at 0, and our emitter, it's unlikely it's going to be anything below 0. So we can assume safely that our emitter is somewhere above our base, and in fact it turns out it's more than a threshold above our base, and so we're actually in active mode. So Q1 and Q4 are inactive. You can go through the same analysis for Q1 and you'll find out the same thing. Now that we know that Q1 and Q4 are in active mode, we can replace them with their equivalent circuits. Remembering that Q1 is an NPN, so we replace it with this equivalent circuit, and that Q2 or Q4 is a PNP, so it gets replaced with this equivalent circuit. Now let's take a look at our simplified diagram with all of these devices replaced with equivalent circuits. Here I've simply replaced this control input with its own source, simply to reaffirm the fact that this is a separate control input. It doesn't have to be tied to 10 volts. We've just tied it there because that's how we'd like to control the motor. And we've tied our second control input to ground. So if we're trying to find out what our motor current is, let's just find the voltage here and let's find the voltage here. So our first voltage, we'll label that A. We have 10 volts minus 1 diode drop across our diode, which is going to be 0.8 volts in our case. Then if we look at our node B, we'll label this B up here. Well, we have the diode drop across 1 diode, and that's what the voltage here is going to be. So if we're looking at the voltage across our resistor, we're simply going to get 10 volts, so we're going to have A minus B. 10 volts is minus 1.6 volts, and we're going to get 8.4 volts is the voltage across our resistor, or our motor. So if we calculate the current for that, we can just assume about 2 ohms for our motor resistance, which is likely what you got in lab, or somewhere around that. We'll see that our I motor is going to equal 8.4 volts over 2 ohms is going to equal 4.2 amps. That's obviously quite a bit too high. We're not going to be able to supply 4.2 amps to our motor at its maximum locked wheel case. It's simply not going to happen. In fact, a current that high may even harm our BJTs. So we need to find some way to limit this current, to push it a little bit lower. And you can see that what the issue really was that the difference between voltage A and B was really high. We had 8.4 volts difference. So if we could reduce voltage A and increase voltage B, we'd have less voltage across that resistor that's modeling our motor, and we'd have less current. So how do we do that? Well, a simple way is to simply add a resistor before the base of both of our PNPs, or both of our BJTs. What's that going to do? Well, we're now going to have an additional voltage drop across there, and an additional voltage drop across there. That's going to push this voltage down, which is going to push this voltage up, which is going to push this voltage up, increasing this B voltage. And here it's going to pull this voltage down, which is going to pull this down, which is going to decrease this voltage. So adding those two resistors on our bases are going to decrease voltage A, increase voltage B. It's going to reduce this voltage difference and give us a lower current. So let's see how that looks in circuit. Here again we have our motor driver. We've simply added base resistors labeled RB to both sides. Again, we've taken one control input and tied it to 10 volts, and our other control input and tied it to ground. And we can go through the analysis of the operating modes for each of these 4 devices, but it turns out that it's the same. Q3 is in cutoff, Q2 is in cutoff, Q4 is inactive, and Q1 is inactive. So again, let's replace these with their equivalent models, just remembering now that we have a resistance on the base of each of these. So once we've replaced these with their equivalent circuits, we end up with a diagram like this. Again, here's one control input, and here's the other. And let's just do the same thing where we add up voltages. In this cases, let's just sum voltages around this loop. We know voltages around that loop are going to have to sum to 0. So we get 10 volts. We're going to have minus IB1RB minus, I'm just going to call it VB for the drop across that, minus our motor current times our motor resistance, minus another diode drop, minus IB2RB is going to equal 0 volts around that whole loop. And we can simplify this a bit, but first let's take a look at IB1 and IB2. Now we'd really like to get rid of at least one of these, so let's take a look at them in circuit. Let's take a look at the current right here and the current right here. They have to equal each other, right? They're just going through a resistor. So this first current, that's going to equal IB1, current coming here, plus what's going to be beta IB1, so this IC. And that's going to have to equal the current over here, which is IB2, plus beta IB2. Now these two devices have the same beta, so you can see if beta is the same on both sides, we're going to have IB1, 1 plus beta, is going to equal IB2 times 1 plus beta, and IB1 is going to have to equal IB2. Additionally, and we'll just keep it here and remember it, IB times 1 plus beta equals the current through here, so that equals our motor current. But immediately we can see IB1 equals IB2, so I'm just going to write them as IB. So simplifying a bit, we have 10 volts minus IB, and then we have two of them, so 2RB, minus 2VB, and let's throw the IMRM on the other side. This is going to equal IMRM. Now we'd like to get rid of IB in this equation down here, so let's simply replace it by this expression we've already seen up here. We know that IB times 1 plus beta equals IM, or equals our motor current, so we can say that IB equals IM over 1 plus beta, and we'll end up with 10 volts minus 2RB over 1 plus beta IM minus 2VB equals IMRM. And here you can see we've only got things that we either know or that we want to solve for in this equation. We know VB, and that's simply the diode drop, and that's going to be 0.8 volts. You can find that in the data sheet for these devices. RB is going to be what we solve for, so we're going to choose that. Beta is in the data sheets for these devices. IM, we're going to set that to some value. So remember, this is the maximum current we want to allow. So we're going to choose 1 amp. We want to allow at most 1 amp. But really you could choose any current. And the RM we've solved for in a previous lab. So everything's known except for RB, which we're going to determine. We're going to solve for RB now. So starting from where we left off on the last slide, we can put most of this stuff onto the other side of the equation. We'll end up with 2RB over 1 plus beta times IM is going to equal 10 minus 2VB minus IMRM, and we can multiply this side by 2I, or by 1 plus beta over 2IM to get the RB equals 1 plus beta over 2IM times 10 volts minus 2VB minus IMRM. There we have our expression for RB. So now we simply select the maximum motor current that we're going to allow, plug in all the other constants that we know, and we end up with an RB needed to limit the maximum current through this motor driver. Now once we've selected RB, we simply put it in circuit. Remember, these are our two control inputs, so we're going to connect those somewhere between 0 and 10 volts, and we have a motor driver. Our output's going to be some variable voltage, which is going to drive our motor, somewhere between minus 10 and 10 volts, and all the power for that is going to come from our voltage rail. So we're going to have power drawn from our voltage rail, not from our control signals, which is exactly what we wanted. So we can hook this up, and then once we have it working, we can deal with making a controller, which is going to generate these voltage signals, but that'll be in a future lab.